Hello, everyone, and welcome to today's seminar hosted by the International Inequalities Institute at LSE. My name is Javier Jara, and I'm an assistant professor and research fellow at the III. I am very pleased to be here in today's seminar titled Very Simple Models of Economic Inequality and Ways to Solve It, which is part of the III's Inequalities Seminar Series. Today's speaker is Professor Jean-Paul Faguet. Jean-Paul is professor of the political economy of development in the Department of International Development and a faculty associate at the III. He is also chair of the Decentralization Task Force at Columbia University's Initiative for Policy Dialogue. As usual, there will be a chance to ask questions after the presentation. We will be taking questions both from the in-person audience and the online audience. So now I hand the floor to Jean-Paul.
Great, thank you. I'm going to let everyone in. Okay, excellent. Thank you. Thank you for a very kind introduction. Thank you for all of you for coming here. So this is about very simple models of economic inequality based on agent-based modeling, which is something which is not very common amongst economists or political scientists. And for me, it would mark a big departure methodologically and also thematically in terms of what I've done during my career. So I really mean it when I say this is super preliminary work. I'm not entirely sure what I'm doing. And I long for feedback from people who know more about inequality and about people who can cast a wary eye on the method of agent-based modeling as I'm trying to apply it to this topic. To tell me, is there anything here? So it's entirely possible, and I really mean it. I'm at a stage in my career when I really absolutely mean it. This may be fun and games and provocative, but there's nothing there in terms of a paper or an academic publication. Or maybe there is something there, and I'd be grateful for feedback if, either way, and if there might be something there on how to do it. All of this comes out of a wonderful sabbatical that I spent partly at the Santa Fe Institute in New Mexico, which is full of mathematicians, computer scientists, physicists, and others, and one of the hotbeds of the development of agent-based modeling over the last 25 years or so. So because how many people here know, just the temperature of the room, how many people here are familiar with agent-based modeling? That you have a reasonable sense of what it is? I would expect few. All right, like 2 or 3? Okay, so let me go super quickly. I'm not going to explain them, but sort of to introduce, some basic characteristics and how they differ from what most of us normally do. So the best way, I think, to an audience like this is to contrast them with representative agent models. Representative agent models are what most of us do all the time in economics and political science and other disciplines. So representative agent models have one or a few representative agents. This goes back to Marshall in 1920, his principle of economics, which he said was an analytically expedient way of moving forward. So for example, the typical consumer, the typical firm, or a median voter model, right? So in political science, a median voter model is a classic representative agent model. Its top-down structure is predefined, right? Whether it's economic structure, industrial structure, class structure in social policy or political science, informal versus formal sector is predefined at the beginning of the model, and then you're looking for equilibrium characteristics of marginal changes in that structure. The focus is on characteristics of an equilibrium and deviations from it, right? This is how we proceed. So from political science, the workhorse model that goes back to the 1950s, the median voter model, where you pre-specify an axis and you have people with conservative views and people with liberal views, and the median voter is in the middle. And as the median voter shifts, so the entire model equilibrium shifts. The way in which you solve this is analytically, right? You solve a system of equations or something along these lines, or you solve a game using game theoretic methods. Now, a large literature for over 30 years has been pointing out the limitation of this. Is an influential paper, sort of overview paper in the Journal of Economic Perspectives from 1992, asking who is this representative agent and how do we interpret this? What do they represent? Who or what do they represent? What does this mean to be modeling things in this way? So, and just, truth in advertising, I've always worked in this way myself. This is from my very first paper that probably got me this job that I still hold here on decentralization. So it's the objective function of a local government, and you take first order conditions and solve, et cetera. So, I'm not, if I seem throughout this presentation, if I sound like I'm attacking other people, I'm not. I'm thinking, should I go beyond what I also have always done? And is this a useful way of going forward? So what are these agent-based models? They're based on many heterogeneous agents that interact with each other. Right? Individuals are multi-dimensional beings. They can be individuals like each of us, or an individual agent can be a household or a firm, or it can be a country, right? So you specify how to interpret the agent in the model. So if they're individual people, which they more often are, then you can vary the heterogeneity in terms of age, size, wealth, weight, metabolism, vision, strength, their DNA complement, how you can have people interact and literally procreate and exchange DNA, and their offspring have DNA from both parents. They're computational models, and you can code all of this in as many dimensions of heterogeneity as you wish to code. They're non-optimizing. So we don't solve a system of equations assuming an equilibrium. You begin with the individuals in some base state, and you let them interact, and then you wait to see if you get to something that would be a broad analog of equilibrium or not, and many models don't. So I'm going to be talking about stationarity, where you don't get significant deviations after some long period of time, as my equilibrium-like concept. But it's not strictly an equilibrium, where equilibrium means nothing changes, right? But it's oops. Oh my goodness. Did I just hit this by mistake? All right. There's no central authority. All right, so they're non-optimizing, heuristics govern decisions. This is computationally tractable, not just for my computer, but also for the agents, right? So it's not requiring agents to have perfect information and to be optimizing every decision throughout the day. They operate by rules of thumb. There's no central authority. So in Walrasian equilibrium, in the cornerstone of microeconomics and welfare economics, there is this mythical Walrasian auctioneer that gathers together all prices and all quantities and plots supply and demand and finds the market clearing combination, and then the market clears, right? This has never been observed in any real economy in the world. It's sort of an interesting construct, a curious construct, given that markets are meant to be decentralized. You need this central Walrasian figure to make it work theoretically. So these models don't require anything like that, because individuals are interacting with one another, and you may get local deviations from the conditions of stationarity elsewhere in the model, and that's perfectly normal, because you're also modeling, or you can model space. So it's a bottom-up analysis. You can, as I said, you can model the environment explicitly. And the most interesting thing about this, perhaps, is its structure emerging. So you begin with a model of, let's say you're modeling a country that has 10 million people. So you begin with 10 million agents. And then the structure, like the firms, are not assumed from the beginning. They emerge from the interaction of the agents. Some big firms, some small firms, some firms that have large amounts of capital, some firms that are pushing forward the technological frontier, et cetera. That all emerges from the interaction of the agents, which again is based on heuristics. The collective characteristics emerge from these interactions over time, so time is an explicit factor in all of these models, as you'll see shortly. So a few simple rules can have startling social effects. So, I like to illustrate this with the behavior of starlings. The thing about starlings, okay, I'm just going to talk loudly for a second. Starlings don't have any centralized intelligence that is coordinating direction, right? Now, many people believe, especially outside seminar rooms, very smart people like all of you. This is from an environmental NGO. If you read the comments on the environmental NGO, okay, we don't need the inspirational music. Thank you. You will see that many people take this as proof of God. Yes. How is it possible that these starlings can be doing such beautiful things without, when each one literally has a bird brain? Like how is this possible? So there must be some central intelligence, and so the central intelligence must be God. Let me not be the one to kill God in the seminar. I have no view on that in particular. I do, but I'm not going to tell you. But you don't need God to explain this. Yes? Because I could, for lack of time, I'm not going to, but afterwards I'm very happy to. I can show you another agent-based model on the same software that I'm going to show you in a moment, where each one of these bird brains has 3 or 4 heuristics. And when all of them have the same heuristics, they flock in this sort of behavior. So you take away the heuristics one by one, and then you get random behavior where different starlings are flying in random directions and even bumping into each other. As long as each one has literally something like 4 heuristics, then you get this beautiful flocking behavior that looks like this, right? Not the sunlight and the clouds, because my computer is not that fancy, but you get the same sort of dynamics. So, okay. So is it part of a revolution in the social sciences? I put a question mark on this. Many people assert that it is. It allows us to model boundedly rational, non-optimizing behavior in a way that's really straightforward and very simple. The mechanics of it are very simple in the way that the analogous conventional modeling, top-down analytical models are very difficult to deal with. It also goes hand in glove with the data revolution, because you can now build agent-based models with thousands or millions of agents, and you can code them up with real observational data from individuals' mobile phones as we wander around town. That's collecting information on how quickly we move through the street and whether we're shopping or working or at home, etc. And you can load that information into the agent-based models and actually start to model society. And also, of course, the plummeting costs of computing. Now, these models have had enormous success, for example, in the world today already. It's sort of curious that economists really don't, most people haven't heard of them. When I say agent-based models, people say, well, maybe I read about that once, but they don't seem to know, and they don't pay much attention. They've been hugely successful modeling traffic flows in jams. So today, the leading traffic models in the Western world are all based on agent-based modeling. Before, traffic used to be modeled as fluid dynamics, right? As a continuous fluid moving through pipes was how we modeled traffic flowing through a city. It turns out modeling individual cars, any one of which can deviate at any point, is a much more realistic and therefore successful way of modeling traffic, right? Epidemiology, models of smoking, drug addiction, COVID-19. There are a huge number of APMs in finance. So here's a fun fact. Decimalization of NASDAQ happened not that long ago, about a generation ago, because NASDAQ, if you're as old as I am, you remember, and you care about this kind of thing, you remember that stock prices on NASDAQ used to be quoted in 8ths and 16ths of a dollar. And at some point the government said, all right, this is kind of confusing and you're introducing distortion, so decimalize. The owners of the NASDAQ exchange, which I think is in Chicago, were worried about this, and so they commissioned some studies, and they finally thought the way to do this, because we're worried about local turbulence in particular bits of the market, maybe in small capitalization markets or people with lower information. So they commissioned a full-blown agent-based model of the entire market of all NASDAQ activity, and they loaded it up with proprietary NASDAQ information that was not public. And they ran this model and figured out how their decimalization, what effects the decimalization was likely to have and how to make it smoother. And then they decimalized, and it was a big success. And you're beginning to get large-scale models that represent entire economies. So here are a couple of pieces by Rob Axtell by himself and with the co-author Omar Guerrero, where they're modeling the entire American economy. Right? So they begin with 120 million agents who are the workers in the American economy. And these people begin as individuals, and then they self-assemble into 6 million firms that have characteristics that look like the American economy. So you've got Apple, and you've got tiny mom-and-pop shops on the corner, and everything in between. And they parameterize the model such that once they start running it over iterative time periods, you get that emergence, and then the model starts to look like, with backward-looking data, it looks like the way the American model's been behaving recently. And then you can, of course, once you parameterize it that way, you can project. Okay, so the last point to stress is, and again, this is my sort of initial steps into this field, is that APMs seem to be our complement. It's not a substitute. So the whole revolutionary thing, it kind of feels like people are saying it's going to sweep away the way we've done economics and politics. I don't think so. I think is an interesting complement if you can do something analytically in the traditional way you do it. It's easy and you can get an answer, then do it. It's very powerful. It tends to be more transparent, but there are lots and lots of problems that are not susceptible to that sort of thing, or that are just very costly to figure out that way. And so ABM should be an interesting complement. Okay, so let's start now. Let me actually start presenting an ABM of inequality. Let's start with a simple barter economy, which is a give a dollar, get a dollar economy. Right, so you know, I give Chico a dollar, he gives Mohammed a dollar, he gives Ken a dollar, and so on. And every time period, somebody gives someone else a dollar, and everybody in the room is receiving. Or to be more precise, because we're going to introduce a random element, which I'll explain why in a couple of slides. In each period, everyone in this economy, so everyone in this room, gives a random other person a dollar, or they give a good that has a value, some good or service that has a value of a dollar, and all receiving happens. There's a random element, which means that Chico might get $2 from me and from someone else in the room, and I might get 0, or I might get 3, right? Because it's random. In every period, it's random. Everyone has to give up a dollar. The model is saying this is how it works, but to whom is randomized. So the simplest kind of barter economy that has or exchange economy that has a random element. So my questions are, how much inequality is due to purely random market forces, right? Because we're not talking about any kind of human capital, physical capital, any sort of resource advantages, locational advantages, economies of scale, or anything there. All the agents are absolutely identical in every way. And the only thing going on is the exchange and there's randomness. So, and can simple policy tools reverse it? So let's start. This is a screenshot from the software I'm going to show you in a moment, how it works. I'm going to start with just, you know, to do it very quickly, a very simple toy model with, I think it's 500 agents. Yeah, 500 agents. They're called turtles in this software for historical reasons. The physicist who came up with the software like turtles. I don't need to put off. When you see turtles in the agents. So this is the initial histogram of wealth. I'm beginning with 500 agents with exactly identical wealth. Everybody at the beginning, and this is just my decision as a modeler, everybody has exactly the same complement of resources. Everybody has the same endowment, right? So now the question is, what is the distribution of wealth going to look like in this very, very simple exchange or barter economy when we move it forward a large number of periods? So let me ask you, what is your guess? What is your intuition? Well, this is what the distribution looks like now. You can see that the wealth of the top 10% is 10, the wealth of the next 40% is 40%, the wealth of the bottom 50%, because everybody has exactly the same wealth, right? So it's sort of trivial. What is it going to look like 100, 1,000, or 10,000 steps into the future? Guess.
More concentration.
More concentration, meaning, so some people getting rich.
Yeah.
Who else? What's another guess?
Stability.
Stability?
And then shares.
Sorry, what do you mean by stability? Sorry, what I'm asking you, what is the histogram going to look like? What is the distribution of wealth? Right now, it's a line, right? So what is that going to look like some large number of periods into the future? Just take a guess. I'm not quizzing. There's no reason why I should. In fact, my socks will be shocked off if anybody knows the answer. Because the answer is not from economics. The answer is from physics.
No.
No. Okay, this is what I thought. Actually, so I'm not as clever as Stephen. At first I thought, well, there's no reason for it to change. Okay, there'll be like slight variation from this line. The line might get a bit thicker, but and then I thought, no, come on, you know, the randomness must mean something, and that's what I thought. I thought a Gaussian distribution, a normal distribution. So let me show you what happens. So this is the software, it's called Logo. There are a number of different softwares you can use. And so I set it up, right? And it looks like, this is what that column looks like. And you can see the histogram. As I said before, it's just a screenshot. And I make it go. And so each one of these green dots is an individual, and they're moving. Now, this axis, the x-axis, is just measuring their wealth. And the vertical axis is measuring, is their identification number. So it's not, it's just like, is it agent number 50 or agent number 60? So you can see them getting further apart in this graph as they exchange. Some people get lucky, and like Chico, they get $2 or $3 in a certain period, but then in another period they get zero, so they fall back and so on, because they're still giving in every period, right? So it's a net loss. And you can see it moving like this. I can speed it up so we make a little bit more progress. And you can see how the histogram is changing over time, right? So it does sort of look like normality, like normal distribution is the thing.
Makes a difference, right?
I'm sorry?
The lower bound makes a difference.
The lower bound makes a big difference. Yeah, we're going to come back to that. That's a big difference. So I have a limiting condition that nobody can fall below zero. And I have an additional condition that if you have less than $1 in your endowment, you can't trade, because each trade is defined to be $1. So if you have less than $1, which you may do for, well, I'll get to that, then you essentially fall out of the market, you fall out of activity. So, okay, so you see that the distribution initially goes through a period. This is after about, where does it say? This is around 200 time periods forward. It goes from complete equality through a phase that looks like it's normal, but when we let it run 50,000 iterations into the future, right? This could be 50,000 years, or more realistically, each exchange period, I would say, kind of feels like in human society, kind of feels like a day, right? Like you might go and exchange $1 every day. So 50,000 days would be 144 years, right? 145, something like that. So you see that this distribution looks very different, and as Stephen points out, the left-hand barrier matters because people start to pile up on the left-hand side at very low endowments. And this is what inequality looks like in terms of wealth shares. So the top 10% of the distribution makes it up above 30% of all wealth in this society, in this economy. I'm going to call this green curve the next 40% down beneath the top 10. I'm going to call them the bourgeoisie, just to call them something convenient. And they do rather well, not as well, but rather well. They get up well above 50% of all wealth. And it's the bottom 50%, which is 50% of the population. The bottom half of all the people in this artificial society fall down around 17 or 18% of all wealth. So they really get hammered. And it's just a straight transfer. So there's no question money is going from the poor to the rich and the richer, to the bourgeoisie and the rich. And notice that the total size of the economy stays the same. This is by construction. At the beginning, it's $50,000, and at the end, $50,000. But the churning just leads to it being distributed differently. So now what's curious is if you look at this distribution, this is actually, and you can see that beyond about, you can see it better in the previous graph. Beyond about 25,000 time periods, you get stationarity where there's very little change. There's like local bouncing around, but there's no significant change in any of the three curves. And this distribution over here with the red arrow is the Boltzmann-Gibbs distribution. So this is a result from a field of physics known as statistical mechanics that anyone who studied physics will have seen. All graduate students learn this is one of the biggest and most powerful results in the field of statistical mechanics. It's the Boltzmann-Gibbs law that defines the Boltzmann-Gibbs distribution, which says, I can illustrate it, and it says something fancy, but I can illustrate it as follows. Imagine that you have a cube, a box of gas particles that are bouncing off each other at constant temperature. What will be, after a large number of time periods forward, what will be the distribution of energy in those gas periods? Because as they bounce off each other, one particle gives energy to the other, and the first particle loses energy, right? So what will the distribution of energy be? And Boltzmann-Gibbs says it will look like this, with a large number of particles at very low or zero energy, and a small number of particles at extremely high energy. And this is it's counterintuitive, which is why it's such an important result in physics. And so these two guys, Dragulescu and Yakovenko, had this. So this is from a whole field. I've been asking economists around the LSE, do you know about econophysics? And almost nobody has any clue what I'm talking about. I had no idea that this existed. So Stephen, again, I should have guessed. I had no idea this existed until I went to Santa Fe and met a bunch of physicists, and they said, oh, but you're an economist, you should know about econophysics. No idea.
It's to do with entropy, doesn't it?
Yeah, it's related to entropy, yeah. Yes, that's exactly right. So these are two physicists. They're Eastern Europeans, but they work in the US and in major universities in the US. And they realize that there's an analog of this box of gas particles in an economic system that is closed and if nobody dies. Right, and so they show, and they model it from first principles in exactly the way that I described, where people exchange in every period, they get a dollar, get a dollar, and you get this distribution. So, and this is by analogy with energy, the equilibrium probability distribution of money is going to follow the exponential Boltzmann stuff, right? So far, I'm not showing you anything original of my own. I sort of a little overview of ABNs, and then I'm sort of relaying a result from this literature. But the interpretation as an economist of this is that random forces generate very high levels of inequality. Because these people here are really very rich, right? And these people here have nothing or almost nothing. Sorry, these people here are around zero.
I mean, if there was no consumption floor, which you built into the model, it would go out to the left-hand side as well. And so there's in fact subsistence built in.
Yeah.
It can't go below zero, so it's actually
Not a little bit artificial.
even not as bad as it could be.
So, and there have been other models that build credit in to allow the poor to survive by taking all those until they get negative wealth. Yeah, and then it's worse. Exactly, that's exactly right.
But with some no Ponzi game condition, there has to be a lower bound somewhere.
Yeah.
There has to be, yeah, that's right. So, the first conclusion is that purely random forces in this super simple exchange economy generate very high levels of inequality. And this has no basis in any sort of anything that we can interpret as political economics, in ability, in effort, in human capital, skills, tools, public goods, resources, anything. It's purely random and it's constant. It's like a trade wind of inequality that is blowing through market exchange all the time, right? And as soon as you start adding these other things, then you might get worse inequality or you might ameliorate it, depending on whether you're adding public goods or you're adding ability or resources. But without any of this stuff, you have natural pressures that come in a sense from physics that are generating inequality. Yes. Sorry.
So just to clarify, once someone reaches zero wealth, can they ever get away from that again? Because they stop trading, right? So
They fall out of exchange. Yeah, they're stuck. And so that I'll show you that in a moment. So now the first, oh yes.
Can you verbalize how the market works here? Just to know whether your market is a market.
It's very simple exchange where in every time period, each one of us, if we're the society, each one of us gives up $1 worth of goods or services to someone else chosen completely at random. And that person is also given up the same amount to someone else chosen completely at random. And the randomness means that some people might receive more than one person's transaction.
But that's not a market, because market is an exchange of equals.
Well, no, it's not.
Sorry?
No, it's not.
$1 for $1, two different goods, but they have.
A market is based on inequality in the sense that I sell you something that you're willing to pay $1 for, that I'm willing to give up for $1, meaning it's worth less to me than it is to you, which is why I stay in
Change
business.
$1 for $1, my initial wealth is equal to my final wealth. In the market you described.
So
What I mean is the variation of wealth you get in every period is based on a randomness which is not based on the market exchange. That's where I'm a bit puzzled.
Yeah. So it doesn't feel like a real market. Yeah, I agree with that. The fundamental construct of the market is that the two people who are agreeing to exchange have different valuations, and that's why they agree to an exchange. If two individuals exchange something that each one thinks is worth exactly $1, they have no reason to exchange.
But
one of them has to think it's worth more.
But then the valuations there that is shown is individual valuations of personal wealth or market valuations. Because if I exchange equivalent, it's a market. And so the variation of wealth is not based on market exchange. It's based on you impose transfers between people at different quantities, randomly. So it's not market.
It's a simple exchange economy. Let me show you the next one, which invokes ability, and then we can talk, because this is so simple that it's almost hard to have this kind of discussion. Once I invoke ability, then we can start to talk about differentials, differentials in value or maybe in valuation, right? And then we can have a discussion. So this is the first thing that I'm going to add that is actually, something of my own. We're going to let ability vary symmetrically around, 3 different margins, a 10, 20, or 30% margin of normal. I've run literally tens of thousands of these models over the last couple of years. And so the one that's most analytically interesting is 30%. So most of what I'm going to show you is 30%, but I'm going to start with 10 and 20 just to sort of make the point. And so the idea is that all of these little green dots who are agents are not identical in every possible respect. They vary in terms of their ability. And the variation is up to a 30% margin, meaning that the least stable person is given a norm of 1.0, right? I normalize normal ability or average ability of 1.0, we can go as low as 0.7 and as high as 1.3. So what does that mean? How do we interpret this? And the expectation for any particular individual, or when you're meeting someone who's anonymous, your expectation is that their ability will be 1. What does this mean in this simple barter economy? Like, I mean, let's say that you and I are going to exchange, and you're just cleverer than I am, right? And so I was going to give you some vegetables, and you're going to give me a loaf of bread that we were each valuing at about the $1 mark. And you look in my closet and you say, forget the vegetables. I'd rather have that leather jacket. I know you never wear it. I've never seen you wear it. Why don't you give me you probably don't care about it. Probably forgot you own it. Give me the leather jacket and I'll give you the loaf of bread. And because you're cleverer than I am, I say, sure, right? So then maybe the leather jacket is a bad example because then that should be a bigger difference. But then, my ability is lower because you can see that this leather jacket has a bigger exchange value in the market. And I accept a loaf of bread in exchange for that. Right? So what happens to this model? Now, what I expected to happen is that inequality would grow bigger and much faster, and that is indeed what happens. You can see that the wealth of the top 10% really balloons. Now, the top 10% is also, as it turns out, one of the things I was curious to see is, will the most capable people be in the richest 10%? And they all are, absolutely. So the wealth of the top 10% really balloons, really jumps up very quickly and reaches very high levels where the top 10% of the population is getting more than 70% of all wealth in this economy. The bourgeoisie does well at the beginning, and then they fall down as the rich get richer, because the rich are taking a larger and larger share of wealth in their trades. And the poorest 50%, again, half of the population just crashes. And after about, now I'm running this for 50,000 periods, after about 4,000 periods, they're down around 5% of all wealth, and they end the period around 1% of all wealth. But yes.
Sorry, just how do you model that in the transactions? And so if I am an average ability person and I give you $1 and you're super smart, it becomes 1.3? Is that what happens?
No, so if you're average, you give $1, and if I'm super smart, I give 0.7. So I've done it various ways. It kind of, you can stick the margin into the giving or into the receiving, and I ended up with.
It's still all transactions, but lower ability people
Lower
give up
ability people
more.
pay more, right?
Give up more than one.
So in any period, you pay 1.3, and your expectation is you're going to receive 1.
So your ability is kind of the inverse of how much you give here.
You can run it both ways. So I've run it as wages and I've run it as prices, and it's absolutely identical because it's such a simple thing. The other thing that happens in this model is that I created economic growth, which completely boggled me. And this is one thing I was not expecting. I thought that this yellow line was going to be fixed. In fact, I hadn't bothered to plot the yellow line. I thought it's going to be fixed at 50,000. And I ran a number of things before I realized that we had economic growth. And so I thought, Jesus, God, this is amazing. How did I do this? And the economic growth comes from, as the model goes forward. In fact, let me show you the next. Let me just show you this while I speak. Yeah, it's this one. And so we set it up. Now here the dots are coded by ability, not by wealth, by ability. The red dots are the more capable people, the blue dots are the less capable people, and you see over time, and they're exchanging the way that I described. I'm gonna speed it up a bit so you can see it faster. And you see over time that there's a segregation. The red people pull ahead. Anybody can get, because the randomness is affecting everyone. But the red people are paying smaller to receive on average one, they pay less than one. Right? And the blue people on average are paying more than one to receive one. And so you see that they pull away from each other, and if I ran it forward 50,000 iterations, then the red people end up over here, and some of them end up stacked up on the right-hand limit, which is just a graphical thing, I can't just fit on the screen. And the blue, I'll show you some of this later on. Already you can see some blue people that are stuck back here on the left-hand limit, on the $1, $1 to $0 limit. Okay, and I can leave this running and go back.
What's the source of the growth?
This, sorry, this.
Sorry, it's-
Oh, yes, yes.
What is the source of the growth?
It is differential trades amongst people who are more efficient or more able. The fact that the low ability people fall out, and so additional trades cost 0.7, for example, but have a value of 1.
I guess it's easy to think of it if what you get is 1.3.
Yeah.
If every time somebody gives you one, you get 1.3, then you're generating more and more wealth, and you get more and more of those 1.3s because you're accumulating everything, something like that.
Yeah,
Yeah.
exactly.
What does that actually mean? I don't know what it actually means. Coming back to it.
It's kind of magical in a sense,
Yeah.
because ability here is just generating extra stuff,
You
magic.
can get a
There's no
Nobel Prize
production.
for it. You can
Hmm?
get a Nobel Prize for it. It's innovation.
You missed this one, Jean-Paul. You got the next one.
So, all right, so let's come back to that, because I have some models, if we have time, on the
Jean-Paul, I just-
production and consumption. Yeah.
Just building onto that, I might be missing something fundamental here, but given that these abilities are relative, the people are dropping out, then doesn't that affect the relative ability of the ones who are left? Like, I'm relatively more able than somebody, but when that person drops out, I'm no longer relatively more, doesn't my relative ability actually diminish?
Yeah, so relative to the
So
society.
the rest of the ones that are left,
Yeah.
I've got my relative ability has decreased.
You're right. In terms of economic activity like exchange and growth, it's expressed in absolute terms. So all of these people that began, let me go back. See what we've got to. All of these people that began the game with abilities of okay, how do I talk about this? Let's say that the people with all right, so the way this here is measuring the average, let's call this ability, the average ability of the top 10% wealthiest people and the average ability of the bottom 50%. So now each one of these people has a fixed ability that does not change over time, right? So because when I created these people at setup, the red people are above, say, 1.15, and the blue people are beneath something like 0.85, I think, or something like that. I mean, there's a specific number in the model. Each individual holds on to that ability, but you're right, the distribution of people who are exchanging changes over time, but I haven't taken that into account yet. But what's going on is that these people, because they're more capable, continue trading with their greater ability, so each trade is worth more to them, it's worth exactly the same amount more to them. But over time, economic activity really concentrates on the red people and the green people, because you can see here, there are almost no blue people left that are still active. Even now, this is 3,000 time periods into this game, and they're, almost all the blue people are stuck at 0. And they're lost.
The question, the point being that if we only have yellow people left and they exchange between each other, they're both giving 1, but also getting 1.3, which means in the end, the ability is not it still matters even though both have the same ability, which should converge to one for ability to be relative. No? Because if not, it's like a productive kind of capacity, which is not exactly the same thing. If both are highly productive, they use one and they get 1.3. But if matters relative ability, if I exchange with someone that already have high ability, I should also get one because the other person also have the same ability as I have. But in this model, to get growth means that even though you exchange with someone with high ability, you still get 1.3. If not, the growth should at some point stabilize once you take out all the other people with low ability.
But are you saying that the growth should stop then at some point because the relative?
Because if only high ability people left and they know how to trade better in the same way, this compensates, so both create one at the end. So you only get growth at the beginning and then it stabilizes. If you plug that into the system.
So I mean, we can figure that out directly. We just run it forward and we see, yeah, okay. So let me move on and thank you for that. Because I hadn't thought of that before. So I could explore that, just pushing these models a bit forward. Okay, so I do the same thing with, so the ones I just showed you had an ability differential of 0.9. So now I go to an ability differential of 0.8 to 1.2. So larger variation in ability. And you see the same kind of thing. And then with more economic growth, and then the economic growth champion of the models I've run, defined in these ways, are with the larger ability differential, which anyway I think is more realistic. You know, these guys who just won the Nobel Prize yesterday, their ability is probably 30% more than average, or maybe even more than that. I actually, okay, I'm just going to that because I'm pure speculation. I mean, they're more than 30% more successful, but how much of it is like pure ability? Anyway, so it seems to me like modeling a 30% ability differential, plus or minus, makes sense rather than smaller differentials. This is the one that gives us the most economic growth. And so as you add more larger ability differentials, you see the way the curves move, right? And the key thing is that the bottom 50% get absolutely hammered. And so down here, they're at 1%. 50% of the population is sharing out 1% of all wealth amongst themselves. Curiously, as this differential increases, the red line does less well. It was above 70%, then it falls to around 67%, and then it falls a little bit further. And the main reason for that seems to be that there are fewer people in the bourgeoisie with whom they can trade. So the bourgeoisie people start falling out as well, with a bigger differential. Okay, and so this is what we've already said before, all of which I just showed you. All the zeros pile up on the left-hand side, can't trade, so they fall out. So now I start invoking tax and transfer mechanisms. So we've got these trade winds of inequality through pure market interaction or pure economic interaction, if you prefer, that are completely random and that are going to lead to a lot of inequality. Yes.
Sorry to interrupt again, Jean-Paul. Just before you get to the state, right? A key thing in old style models that gives you some equality is concavity of production functions. Diminishing returns.
Yeah.
Right? So as you have a certain amount of you keep adding capital to your labor and your land, that capital becomes less productive. Here it's linear. So there's this kind of constraint on you run out of people to exploit in the middle class. But aside from that, you take you're always translating ones into 1.3s at the same rate. There's a linearity there. If you try to impose some concavity, would there be a way to impose some concavity, some diminishing returns?
You could
that would bound.
Yeah.
I think that would have a market-based, and it'd be interesting to see how much.
Yeah, no, okay. No, I haven't tried that, but that's a good idea. Let me just point out, I showed this in Santa Fe to a biologist friend who said, what is the probability of exchange for these different bits of the population? I hadn't thought about it at all. I said, well, it's the same. Everyone, I mean, unless you fall out, everyone otherwise has exactly the same probability because it's built in. Everybody trades once in each period if you're above $1. And he said, that's ridiculous. In any sort of biological system where the thing that you're modeling is procreation, the more successful people procreate more. So you need the opposite sort of function that allows higher ability people to trade more than once in each period and lower ability people to trade less than once, or something along these lines. This is not a comeback to you, because the economic logic of what you're saying is absolutely right, but they're different ways,
Elon Musk
different
is-
things that I can code in.
Elon Musk is with you, no? On the reproduction of highly successful people.
Wait, I have a question. So the blue line is going down. So the high ability people is taking all the wealth from the poor,
Yeah.
right? But why doesn't that happen with the ones in the middle?
With the green ones.
Yes, like they seem, so some fall and some lose their wealth and they go to the bottom in the black box.
Yeah.
But some others still, like I would expect the high ability people to also take the wealth from the middle.
Well, they do. These green people start off, remember, they start off at 40% of all wealth. At the beginning, they jump up very quickly because they're also taking money from the poor, but then they fall back as the rich get richer. So what's going on is that some of these, let's call them green people, some of these green people, the next 40%, are above 1.0 ability and some are below 1.0 ability. And the ones who are below get pushed down in a longer period of time more slowly along with the poor. But others have stayed. Oh, so in fact, let's look at our model. Oops.
Mind the turtle.
So this is the model that's just continued running, and now we're up to 7,900 time period. And you can see that there are now a lot of green people that are stuck on the left-hand barrier and others that are making their way slowly. But some of these green people are up here dancing with reds, right? So the green group is less, in terms of this model, is heterogeneous within itself. Okay, so I'm going to try to push forward quickly because I want to at least get onto the next generation of models, which have production and consumption and resources. So it's far less abstract than these models. Okay, this we talked about. Okay, so sticking with these models, I want to impose tax and transfer, fiscal mechanisms to say, can we beat down inequality, and how much can we beat down inequality with what kinds of tools? What does it require crazy tools or extreme tools to get inequality back down to tolerable levels, or can you do it with common day tools? So I'm going to start off with fully funded models that tax the top 10%. Let's see, we're going to tax the income of the top 10% by wealth. And we're going to transfer to everyone equally in the bottom 50%, and we're also going to fund the public good, which is just the public good that goes into everyone's income function equally for everyone, rich, middle class, and poor, equally, right? So the public good makes all of us a little bit richer in every time period. And it's fully funded, so all of this has to come out of tax. What happens? Well, so inequality is not quite as bad as before. Economic growth is significantly less than before because you're taxing the richest people, and they're the ones whose trades generate the growth. But it's still a very unequal society, right? So the top 10% end up still above 30%. So you've kind of undone the ability, but you haven't undone inequality, the ability effect. So then I try more sophisticated things where I'm really trying to parameterize it, to fine tune it, to achieve the effect that I described. I'm going to tax the top 50% of people, right, by wealth. So the top 10 and the next 40, the rich and the bourgeoisie, I'm going to tax all of them. I'm going to transfer it to some bottom share S, which I'm going to vary to try to figure out what the sweet spot is. And that will fund transfers to this bottom share, and the public good, which again is the same for everyone. Public good by definition, everyone has to benefit from it the same way. And there you can see there are two different models. Now, again, I've run these things, thousands of iterations, and I'm just sort of picking. So then this is a 10-run average for these settings up here at the very top. So the ability differential is 30%. The tax rate is 40% of income in every period. G is worth 15%, so it's equivalent to 15% of income in average income in any period. The transfer is 0.167, and the share, I'm making transfers to the bottom 30% poorest. So from the very poorest up to the 30% mark. And you can see that this combination of parameters really reduces inequality quite significantly. So the top 10% by wealth never makes it much above 13% of all wealth in this model. The bourgeoisie goes from 40 to about 52%. The bottom 50% lose, but they don't lose like they were losing before. They end up around 30%. And this would be this would be of these sorts of models that significantly reduce inequality, this is the growth optimizing model, because you still have a lot of economic growth. And then here, this is the most equal model, the inequality reducing optimum, as it were, optimum, the best one that I found, right? Where the top 10% ends up around 12%, the bottom 50 ends up above 40% of all wealth in society, and the bourgeoisie ends up with something like 46%. Economic growth is less than it was before. You can read that from the yellow curve. Before it was closing in on 500,000. Now it's something like 330,000, something like that. 325,000. But inequality is really, so this is extremely low inequality, right? These sorts of curves, we would interpret this in a modern economy as very, very low inequality. So, next couple of conclusions. From all of these models, ability seems to operate multiplicatively with randomness in terms of market exchange. Ability greatly charges up. Because, one possibility is the high ability people are not going to benefit from the random element of this exchange. And so some of the high ability people will fall down into the poorest, but that absolutely doesn't happen. In fact, it greatly exaggerates the random forces that are leading to inequality. Taxing the top 50% and transferring to the bottom S% greatly decreases the rich by increasing the wealth of the bottom 50%, and thence overall wealth in the economy, because these people continue trading, they don't fall out. And it's much more effective at decreasing the top 10 share than only taxing the top 10. Because when you tax the top 50, you're taxing a lot of the other people that the richest might otherwise be trading with. And so this actually succeeds in depressing their share of total wealth as well, and this is not intuitive. I was not expecting this again. I tried a low tax alternative, so like kind of Tory, Republican, etc. Let's keep taxes to 15% of average income, and you can see what happens. It just doesn't work very well in terms of decreasing inequality. You still have very high inequality. The poor still do spectacularly badly, and it's also not particularly good for growth. In this model, low taxes are not leading to higher growth. Actually, the higher taxes and transfers led to better growth. Okay, so let's move on. So now, in the last couple of minutes, let me just show you very briefly the next generation, and this is far, far more realistic. It's a simple economy that has natural resources, production, and consumption. So we're going to model physical space where natural resources are greater in some places and less in other places. And people can move through, and now the space matters. Because in those former figures that I was showing you, the black field with the red, yellow, and green dots, space is irrelevant. Somebody who's over here can trade with somebody over there as likely as somebody who's right next to them. Space doesn't really exist. The space was measuring their wealth. So now space matters because resources are in space and people move around space and they try to get to the resources. Agents are initially located randomly. They move towards more resources. They have vision. We can graduate how well they can see, how far they can see. They use resources to generate income, including their ability. So using their ability, they transform the resource into something that they can eat. And they have to be able to eat at a level that feeds their metabolism and keeps them alive. If their wealth, if their stock of income, as it were, if their wealth falls beneath their metabolism, they die and are immediately replaced. So it's sort of like single agent procreation. They're immediately replaced with another agent with random characteristics. So there's no inheritance of biological characteristics or of wealth. We can very easily code that in. But for this first set of models, I'm keeping it super simple. The resource replacement can be varied. So if you think of these resources as minerals, well, as soon as you pull them all out, they're done and you're finished. But it could be wheat. And so, the wheat will grow back in a certain number of periods with a certain amount of fertility. So you can vary the grow back time and the grow back, the grain, the grow back stock, the amount of grow back. So what would this look like and how would it work? Okay, so we set this up and now we have a topography. And in this case, the intensity of the yellow means more resources, whether it's minerals, gas, oil, or grain, or rice, or whatever. And you can see the agents, again, I'm just skipping the whole, like no ability. So going straight to these models that have differential ability, again, red or high ability, and blue or low ability, and green are the people in between. And so I'll set it to go, and you see that these rapacious little buggers are denuding the landscape, right? They're eating all the resources and transforming them into food as according to their ability. This ability is sort of an economic ability, which I'm distinguishing from things like how far can they see and what is their metabolism, to try to figure out exactly what it is in this model that is generating the action. So I'm going to let that one go on. And let me go back to here. So as a baseline, now in this case, economic growth is not smooth because it depends on resource exploitation, right? So economic growth jumps up, but it's above some sustainable level, and then it falls, and then the growback is enough to maintain, something roughly at that level, around $90-some thousand in the whole economy. You can see that the poor get poor, but they don't crash like they were doing before. The rich get richer. It's a little bit more varied. Again, the curves are not smooth because of the nature of the economic model. So then I put in, okay, so sorry, these curves are not, the model I just showed you had heterogeneous ability. This baseline didn't. So now I add heterogeneous ability, and I add parameters that mimic the highest inequality societies that we observe in the world today. And as you guys know better than me, some of the inequality champions are South Africa, Brazil, and Colombia, right? In terms of observed inequality. This is World Bank data, this is just the Gini. I know the Gini has problems, etc. But to be very, very quick, what are sort of high Gini levels that I'm going to be able to mimic in these models? Well, so you see South Africa is the highest above 0.6. And then you have another set of countries with kind of moderate, with in between Gini coefficients. So you've got Europe here and the US there, in between 0.3 and 0.4, right? These are just different time periods in between 2010 and 2021. And then interestingly, you've got some fairly sophisticated big-ish economies. So I'm not including very tiny poor places where everybody's equal in their poverty, and I'm not including very tiny, super rich places that live off oil. So this is more diversified economies like the Czech Republic, Netherlands, and Slovenia that nonetheless have quite low Gini coefficients, right? So can we come up with one of these models that looks like that? What would a South Africa-like inequality level look like in my modeling context? And so this is it. These are the variables up here. And this is generating a Gini coefficient of 0.66, which is slightly higher than the observed Gini that we see in South Africa today. And so then the question I'm going to ask is, what would it take to beat this down in this kind of model that actually has production and consumption? Can tax and transfer policies do it in this less unrealistic environment than like the fifth generation models actually do? And the answer is yes. So I run this model and I vary these parameters, having mimicked the South African high inequality equilibrium, and it's stable over time. I then add tax and transfer, and I see that I can push the Gini down in this exact same, otherwise identical country with simple tax and transfer to beneath 0.3. So it's actually slightly lower than France and Germany. Now, I haven't made it very far, I just haven't had time to do this. But I'm betting with myself that I can push it down close to 0.2, i.e. close to the most equal societies on Earth, but I just need more time to sort of find the tools. I think I'm going to just close by saying that in this generation of models, it's metabolism that's doing most of the work. It's the fact that people are going to die if they don't, or rather, it's the fact that they don't save anything because they gather resources and they transform it into food and they eat all of it, and that's why they're poor. It turns out things like productive ability here doesn't matter. It mattered hugely in the first set of models. Here it doesn't matter. Vision doesn't do very much work. And so, is there any point to all of this? is the question that I might close with. Along with, if doing this kind of thing is straightforward with tools that we observe all over Western Europe, why don't we do more of it? Why do we have such high and growing levels of inequality in certain countries of the world? Because it doesn't seem like the mechanics of it are complicated. So there's something, and one comment I got is I need to add a political module. Instead of making it economically more complex, I should add politics to it and try to analyze the decision rules that are leading to these equilibria that feature very high inequality. Okay, I'll stop there.